Hello everyone, my name is Ryo Takashi from the University of Tokyo. Today, I'd like to talk about this project, telemetry. We use passive inductive telemetry to enable a batteryless and wireless ring-shaped keyboard. This work has been done with Fukumoto Masaki from Microsoft and my colleague Janyo Takuya Shuiki and my advisor Yoshihiro Kawahara. As we all know, wearable devices like smartwatch and smart clothes are popular. They notify the message quickly or track their activity constantly. However, they lack of the rich input interface. Because their touchscreen area are very limited, it is difficult to type text. So, previous research has explored wearable input interface. The simple method is track finger gesture like finger drawing and thumb tapping. It is also possible to input text by finger typing like a keyboard. To detect the typing, a series of fingering, it is also called ring-shaped keyboard, has been proposed. Fingering consists of 5 ring-shaped sensors and 1 wristband-shaped reader. Each sensor detects the finger typing and sends the information to the reader via wire or wireless channel using body coupling. It is known that ring-shaped keyboard supports high-speed text input with small typing force. However, the previous wireless ring-shaped keyboard requires battery to each ring because the rings need to empower the components like microcontrollers or wireless communication modules. These cause 2 problems. First, the battery is bulky, so this makes the users uncomfortable to wear the 5 rings. Second, the battery-equipped rings require the user to charge them manually. So, what can we do to push the boundaries of the wireless ring-shaped keyboard? The simple answer is to remove the battery from the ring. Here, I introduce the first batteryless and wireless ring-shaped keyboard named Telemetry. Telemetry consists of 5 batteryless ring-shaped sensor coils and a wristband-shaped reader coil. Because the ring and the wristband are coupled inductively, wristband can receive the sensor information wirelessly. And telemetry supports text input by finger typing like this. By decoding the typing sequence to the characters, we can type text like with. To make the batteryless ring-shaped sensor and communicate with the sensor wirelessly, there are some methods. Energy harvesting seems to be the intuitive way. Using harvesting energy, the sensor can empower the components like microcontrollers and wireless communication modules. However, it is difficult to get enough energy anytime and anywhere. Although vibration caused by typing seems to be a useful energy source, we cannot store enough energy to empower the components. So, wireless power transfer is also a promising way. Like Qi-charger, by transmitting energy from the wristband to the ring, the sensor touched on the ring can work without battery. But in our case, the distance between the ring and the wristband is too far, so the efficiency that I measure is under 1%. Because of the very low efficiency, we cannot send enough power to the sensors. Therefore, telemetry uses a passive inductive telemetry. Passive inductive telemetry is one kind of wireless sensing technology, and this mainly uses coil. This consists of 3 components: a passive sensor coil, an external readout coil, and an impedance measurement circuit connected to the readout coil. As you can see, the 2 coils coupled inductively. Because of the inductive coupling, the impedance change of the sensor coil also changes the input impedance of the readout coil. So, the impedance measurement circuit can detect the sensor value wirelessly. Also, the telemetry has 2 advantages. First, The sensor coil does not need battery because the sensor can change its impedance through a passive variable capacitor. As you know, the variable capacitor can be easily designed using passive materials like piezo, thermistor, or force-sensitive resistor. Second, the inductive coupling is robustly human. We use the telemetry to realize the batteryless and wireless ring-shaped keyboard. However, the inductive coupling is very weak because the distance between the ring and the wristband is very long and the size of the ring is very small. The coupling strength that I measure is about 0.05, which is about 1/10 compared to that of the previous ring telemetry. Because of the very weak coupling, the change of the input impedance is extremely small, and the previous telemetry cannot detect the sensor change. So, we need to develop a new telemetry system that is very high sensitive. From here, I will talk about how telemetry works. First, we design a shock-sensitive variable capacitor by combining piezo and varactors. By the typing shock, the piezo generates a voltage and the voltage is applied to the varactors. Then, varactors change their capacitance value depending on the magnitude of the voltage. In our case, the capacitance of the varactors lowers approximately 1 picofarad. Next, we distinguish which sensor coils react to the typing shock. To realize this, we utilize the knowledge the impedance change of the sensor coil can be most clearly appeared around the resonant frequency of the sensor coil. So, we tune the 5 sensor coils at a different frequency from F1 to F5. At F5, the circuit can be simplified in the way that only one sensor coil is coupled with the leader coil because the other 4 sensor coils are off resonance. As I explained before, however, the change of the input impedance is extremely small because of the very weak coupling. To make the change bigger, it seems good to increase the inductance value of both sensor and leader coil. However, the number of turns, the total length of the coil, is limited to the wavelength. If the wire of a coil is too long at high frequency, the wavelength is so small the coils become capacitor. As a result, we need to decrease the number of turns of coil at a high frequency. To overcome the challenge, we use distributed reactance compensation technique, simply called DRC, which can make a coil with a high inductance at a high frequency. The idea of DRC is very simple. To mitigate the limitation of the short wavelengths, it inserts multiple capacitors into the coil. Imagine that multiple capacitors split a single long coil into multiple small coils. Each coil is so short the wavelength scale can be ignored. With this, we can increase the number of turns at a high frequency. In our case, the sensor coil has 2 inductors in series by inserting 2 varactors. Also, the leader coil has 10 inductors in series by inserting 10 chip capacitors. Because of DRC, the input impedance of a leader coil can slightly change when typing occurs. Finally, I will talk about how we take the small change of the input impedance and distinguish which fingers are typed. First, we use a balance bridge circuit. Using this special circuit, the small change of the input impedance causes the change of the output phase. Based on the output of the bridge circuit, next, we calculate a phase spectrum. As talked before, we assign the different frequencies to our 5 rings. So, the finger typing action can be detected independently by tracking the phase change at each resonant frequency. Finally, we pick up the typing action by detecting the sudden phase change and decode the typing sequence to the characters. Here, we explain the working principle of a balance bridge circuit. This is a variation of the Houston bridge circuit, which detects the impedance change. The output can be written using reference load Z-bridge, measurement load Z-in, and input voltage V-in. To detect the small impedance change of the readout coil, we need to increase the sensitivity to the maximum. So, we match the Z-bridge to the readout coil Z readout. With this, V-out can be expressed like this. Notably, the small impedance change Z-in at Fi can be appeared clearly through the phase change of V-out at Fi. So, we can detect the typing action through the phase change. This is the prototype of telemetry. The resonant frequency of the readout coil is 30.56 MHz, and the 5 resonant frequencies of sensor coil are assigned around 13.56 MHz. A USRP emits multiple frequency signals, and the PC connected to the USRP calculates the phase spectrum through the output of the balance pitch circuit and detects the typing action. Here, I will show the typing recognition rate about telemetry. I tested 31 typing patterns. As you can see, the 4 typing patterns showed very bad rate because it is difficult to type these patterns. Try and feel it yourself. Based on the result, I use the patterns except the 4 bad patterns for A to Z characters input as shown later. I'll explain how users type text using the ring-shaped keyboard. As you can see from this table, A to Z, 1 to 9, and symbols are assigned to the different typing codes. Based on the table, the user can input text very fast with small typing force. Of course, I need to improve the recognition rate over 99% to realize the more robust typing input. Finally, I would like to summarize my work. In this work, I introduced telemetry, a batteryless and wireless ring-shaped keyboard. To realize telemetry, I developed very high-sensitive passive inductive telemetry by combining distributed reactance compensation and the balance bridge circuit. As future works, first, we need to improve typing recognition rate. Also, I need to improve a standalone telemetry. Although the current telemetry is connected to the power source, I will re-implement the standard version as true wearable device. Finally, I hope our passive inductive telemetry will be utilized for other wearable devices. Our telemetry has the potential to make them batteryless and wireless wearable device. Our telemetry has the potential to make them batteryless and wireless wearable device. Thank you, and happy to answer your questions.